Hello, this will be a demonstration of proposition 16 from book 3 of Euclid's Elements, which states that the straight line perpendicular to the diameter of a circle at its extremity will fall outside the circle, and into the space between this straight line and the circumference another straight line cannot be interposed. Furthermore, the angle of a semicircle is greater than any acute rectilineal angle, and the remainder is less than any acute rectilineal angle. It's the first time we are dealing with horned angles, angles composed of a straight line and a non-straight line. In this case, we're dealing with the angle of a semicircle, which is contained by a straight line, the diameter, and an arc of the circle. We are given the circle ABC, like so, with diameter AB and center D, some other point there, we'll call it C. And what we have set out to prove is that the straight line perpendicular to AB at the point A, AB being the diameter of the circle ABC and point A its extremity, straight line perpendicular to AB at the point A falls outside the circle ABC, and between it, that is the straight line perpendicular to AB at point A, between it and the circumference of the circle ABC, another straight line cannot be interposed. And finally, the angle of the semicircle ACB, so that's this semicircle right here, is greater than any acute rectilineal angle, and the remainder is less than any acute rectilineal angle. What Euclid here means by the remainder will be revealed shortly. Now first, if this straight line, that is the straight line perpendicular to AB at the point A, does not fall outside the circle ABC, then it either falls within or on the circumference. So first, let it fall within as the straight line AC, like so. And we know that AC is perpendicular to AB. We shall join the straight line DC by postulate 1. Now we know that DA is equal to DC by definition 115, they're radii of the same circle. And their being equal means that in this triangle DAC, the angles which they subtend will also be equal. That's proposition 1,5. And so that we can say that the angle DAC is equal to the angle DCA. Now we know from the first step that the angle DAC is a right angle, and so any angle that's equal to it will also be a right angle, so that the angle ACD is also a right angle, like that. And if we add these two together by common notion 2, we can say that the angle DAC plus the angle ACD equal two right angles. Now the angle DAC plus the angle ACD equals two right angles, but we also know by proposition 117 that if in a triangle any two angles be added together, they will be greater than the remaining angle. And so we know that the angle DAC plus the angle ACD must also be less than two right angles. And so we see that the angle DAC plus the angle ACD must simultaneously be equal to two right angles and less than two right angles, which is absurd. And so we can say that the straight line perpendicular to AB at the point A will not fall within the circle ABC. So this straight line here, AC, is not the straight line perpendicular to AB at the point A. So we can do the opposite. So we can get rid of it. Similarly, we can prove that it won't fall on the circumference either. And so falling neither within the circle nor on the circle, it must fall outside the circle. And given that this is the case, we'll then make this straight line. At the point A, we shall make the straight line AE perpendicular to AB, like so. We can do this by proposition 111. Now, if another straight line can be interposed between AE and the arc CHA, the arc CHA being this arc here, right there. If another straight line can be interposed between AE and the arc CHA, well, then we'll let this straight line be so interposed. What it means for a straight line to be interposed is that in this space, another straight line can be put sharing the point that bounds the space. What I mean by that is that the point A here bounds the space between the straight line EA and the arc CHA. And so any straight line interposed in this space must fall on the point A. That's what interposition means. And so we'll let this straight line interposed between the straight line EA and the arc CHA exist. We'll call it FA. Excuse me. Now, at the point D, or from the point D, we shall let the straight line DG be made perpendicular to FA, like so. And so we have a right angle there, I suppose. We can do this by proposition 112, the point D not being on the straight line FA. We have to use 112 and not 111. Now we know that the angle AGD is a right angle. We made it that way in the previous step. And we also know that the angle DAG, so this angle right here, DAG, must be less than a right angle. We know this because the angle DAE is a right angle. We made it that way in step 5. And so any angle that is a part of it must be less than a right angle. And we see that the angle DAG is a part of the angle DAE. And so DAG must be less than a right angle. It's by common notion 5. And so the angle DAG must be less than the angle AGD. And this also means that the angle AGD is greater than the angle DAG. Now the greater angle being subtended by the greater side, that's proposition 119. We know that the straight line AD, which subtends the angle AGD, must be greater than the straight line DG, which subtends the angle DAG. So what we're saying is that this straight line here, AG, must be greater than this straight line here, DG. So AD is greater than DG. Now we also know by definition 115 that DA and DH, being radii of the same circle, must be equal. And so the straight line DA equals the straight line DH. And by property of magnitudes, we can then say that the straight line DH is greater than the straight line DG. So we see that the straight line DH is greater than the straight line DG, but we also see that the straight line DH is a part of the straight line DG, so it must be less by common notion 5. And so DH must be simultaneously greater than and less than the straight line DG, which is absurd. And so we can say that another straight line cannot be interposed between the straight line AE and the arc CHA. So this straight line here simply does not exist. Okay. So, finally, if there is any acute rectilineal angle greater than the horned angle CAB, this angle is CAB, so it's that angle right there. If there is any acute rectilineal angle greater than it, and if there is another acute rectilineal angle less than the horned angle CAE, so we see what Euclid means by the remainder. We have this whole angle EAB, and it has been divided into the horned angles CAB and CAE. And so if there is any acute rectilineal angle greater than the horned angle CAB, and another acute rectilineal angle less than the horned angle CAE, we'll let these angles simply exist. And we'll let them exist as the angle FAB and the angle FAE, like so. And so FAB is greater than the horned angle CAB. We also see that the angle FAE is less than the angle CAE. We're simply going to let these angles exist. Now, the only way these angles can exist, the only way these angles FAB, or the only way these rectilineal angles FAB and FAE can exist is if this straight line FA is interposed between the space EA and the arc CHA. That's the only way that this can work. And so we see that FA is interposed between the straight line AE and the arc CHA, but we also know, by step 10, that no such straight line can exist, that there can be no straight line interposed between the straight line AE and the arc CHA, and so FA must be simultaneously interposed and not interposed between the straight line AE and the arc CHA, And this is obviously an absurd thing. And so we can say that there is no rectilineal angle greater than there is no acute rectilineal angle greater than the horn angle CAB, and there is no acute rectilineal angle less than the horn angle CAE. Excuse me. There we go. These lights automatically turn on. It's quite annoying. And so these angles don't exist. And so then we can say that the horn angle CAB is then greater than any acute rectilineal angle, and that the horn angle CAE is less than any acute rectilineal angle. Now, this all being what we've set out to prove, we are done with the proposition, therefore, etc., QED. I really do quite like this proposition. It's very nice. Oh, I forgot the aporism. The aporism's like more important than the rest of the proposition. It's hilarious. Okay, so aporism. This aporism is that the straight line perpendicular to the diameter of a circle at its extremity touches the circle. Oh my goodness, cannot believe I forgot to do that. I often forget to do aporisms though, so I guess it's not the most shocking thing. So we see how this follows because the straight line here, AE, is perpendicular to the diameter AB at right angles. And we see that it neither falls within the circle nor does it fall on the circle, and both falling within the circle and falling on the circle count as cutting. And so this straight line here, AE, does not cut the circle, but it does share a point, it does meet the circle, and so if it does not cut it, the only thing left is that this straight line, AE, then touches the circle. And so we can say that any straight line perpendicular to the diameter of a circle at its extremity, therefore touches the circle. This aporism is extremely, extremely important, so certainly you should remember it. Now, I have nothing more to say about this proposition, so I will end the video here and move on to 3.17.